Welcome to TalkTensors. It is the podcast for the graduate student, the researcher, and the insanely curious mind that just can't get enough of the bleeding edge of machine learning. I'm your host, and I am ready to get my mind blown today.
It's good to be here. And honestly, if you're looking to have your mind blown, you picked the right day. We are looking at a paper that I think people are going to be referencing for a very, very long time.
I think you're right. Today we are doing a deep dive into a paper that essentially challenges the undisputed king of modern AI. And we all know who that is.
The transformer.
The transformer. For almost a decade, it has been the answer to everything. Text, vision, protein folding, you name it, you throw a transformer at it.
It's the default. It's the architecture you have to beat.
But today we're looking at a paper titled Mamba, Linear Time Sequence Modeling with Selective State Spaces. It's by Albert Gu and Tridow.
And you really have to pause on those names. These are two absolute heavyweights in this specific niche of efficient sequence modeling.
Tell us a bit about that.
Well, Albert Gu has been pushing the boundaries of state space models for years. I mean, S4, H3, Hyena, that's his lineage. He's been on this quest. And Tridow, of course, is famous for flash attention.
The person who made long context transformers practical in the first place?
Exactly. The master of hardware-aware algorithms. So when these two get together, you know something big is happening.
It's like a superhero team up for ML efficiency.
It really is.
And the premise here is, it's audacious. They're proposing an architecture that matches transformer quality, which is the holy grail, but does it with linear scaling.
Linear scaling. So just to spell that out for everyone, if you double the length of your input, you double the compute, not quadruple it.
Which could potentially unlock, say, million token context windows on consumer hardware. Something that is just a fantasy right now.
It is a massive claim because for years we've had this trade-off, this uncomfortable choice. You could have the quality of a transformer, but you paid for it. You paid with that quadratic compute cost. Yeah. Or you could have the efficiency of something like an RNN, but the performance just wasn't there. Not on dense, complex data-like language. Mamba is claiming to break that trade-off, to give you both.
Okay, before we get into the mechanics of how Mamba actually works, and I really want to get into the nitty-gritty of this selective state space thing, we need to set the stage. We need to talk about the era we are living in, the era of the transformer.
Right. So if we rewind to 2017, the attention is all you need. Paper drops. And it's not an exaggeration to say it changed everything.
It really did.
It introduces the self-attention mechanism. And the reason this took over the world is that attention is just incredible at routing information. It allows every single token in a sequence to look at every other token all at the same time.
It's like a room full of people where everyone can whisper to everyone else simultaneously. Yeah. No matter where you are standing, you can hear what the person in the far corner is saying if it's relevant to you.
That is a perfect analogy. It's a fully connected graph. But here is the cost of that party.
The cost?
If you double the number of people in the room, the number of possible conversations doesn't just double.
It quadruples.
It quadruples. It scales quadratically. In notation, that's all LL2, where L is the length of the sequence.
Which is fine if you have a short sentence, a tweet. But if you have a whole book, a medical record.
The costs explode. And deeper than just the raw compute, you have the key value cache or the KV cache. This is the real killer for inference.
Explain that. Why is the KV cache such a bottleneck?
When you generate text autoregressively, like ChatGPT does, one word at a time, you have to store the history of everything you've seen so far. You store these key and value vectors for every previous token.
So you can compute the attention for the next word.
Exactly. That cache grows linearly with your context, which sounds okay at first, but the calculation over that growing cache is still quadratic. It becomes prohibitively expensive to have really, really long context. You just run out of memory and you run out of patience.
And this isn't a new problem. I mean, people have been trying to kill the transformer, or at least fix this quadratic bottleneck, basically since the day it was published.
Oh, yeah. We sometimes call it this subquadratic graveyard.
The graveyard. Love that. So who is buried in this graveyard?
Well, it's not that the ideas are dead, but they haven't dethroned the king. You know, you have a whole family of linear attention models which try to approximate that dense attention matrix.
But they were lossy.
They were lossy. The performance was never quite there. Then you had recurrent models try to make a comeback, like RWKV, very clever, but again, struggled to match transformer quality.
And then you have the more direct predecessors to Mamba.
Right. You have H3, Hyena. These were also based on state space models, and Albert Gu was a key author on those too.
So he's been iterating on this for a while.
He has, and H3 came very, very close. But the consensus in the field for years was always the same. Sure, these linear models are fast. They're great for long, continuous signals like audio. But on language, on the really dense, complex, discrete stuff, they just don't match the transformer.
Until now.
Until Mamba.
So let's lay out the thesis here. If you had to boil it down to one sentence, what is Mamba doing that everyone else missed?
Mamba introduces a selection mechanism to state space models. This allows the model to selectively remember or ignore information based on the input itself. And this is the critical part. It pairs that idea with a hardware-aware algorithm that makes the whole thing run efficiently on modern GPUs.
Selection. That's the word of the day.
Yeah.
Okay, let's unpack this. To understand Mamba, we first have to understand what it's fixing. We need to talk about state space models, or SSMs.
Right.
Now, I know the math can get heavy here with differential equations and all that, so let's keep it conceptual. What is an SSM?
So a structured state space model, or S4 as it was known, essentially maps a 1D sequence, think of a waveform or a string of text tokens, to an output sequence. And it does this through a latent state, a hidden state.
The model's memory.
You can think of this latent state, we call it EHAT, as the memory of the system. It's the scratch pad where the model keeps track of what's happening.
Okay.
Now, the magic of SSMs, the reason people got so excited about them, is that they have this dual nature. On one hand, you can view them as a recurrence.
Like an RNN.
Exactly like an RNN. You process one token, you update your state, you output a result, and then you move to the next token. This is amazing for inference.
Why?
Because it's constant time and memory per step. You don't need to look back at the whole history. It's all compressed into that fixed size state.
Right. Unlike the transformer, which has to look back at that massive, ever-growing KV cache, with an SSM, the state size is fixed. Whether you process 10 words or 10 million words, the memory takes up the same amount of space.
Correct. But. There's always a but.
There's always a but.
Historically, recurrence is slow to train. Because you can't parallelize it, it's inherently sequential. You have to wait for step 1 to finish before you can even start step 2.
It's sequential. And GPUs, the things we use to train these models, they hate sequential. They are built for massive parallel operations.
GPUs absolutely hate sequential. But here's the trick. Here is the other side of that dual nature. SSMs can also be computed as a convolution.
Like a CNN.
Kind of. If you know the whole sequence ahead of time, which you do during training, you can unroll the recurrence and express it as one big convolutional filter. And we have incredibly fast ways to compute convolutions.
The fast Fourier transform, FFT.
Right, exactly. Using FFTs, you can compute the whole thing in parallel. So you get the best of both worlds, right?
So it seems. Fast parallel training like a CNN, fast sequential inference like an RNN. What's the catch?
The catch is a massive constraint. To make that convolution trick work, to use the FFT, your model has to be LTI, linear time invariant.
Linear time invariant. Okay, let's break that down. In simple terms, what does that mean for the model?
It means the dynamics of the system, the matrices, we call them Euler, $8, $T, that define how the state updates and what the output is. They have to be fixed. They are constant. They do not change over time or based on the input.
So wait, you're saying the model applies the exact same filter, the exact same rules to every single token in the sequence, regardless of what that token is.
That is exactly it. I like to use an analogy. It's like looking at the world through a pair of sunglasses with a specific fixed tint. Everything you see, every person, every car gets processed through that same tint.
You can't decide to take them off for a dark room.
No, you can't decide, oh, this part is dark, let me use a lighter filter, or this part is bright, let me use a darker one. You are stuck with the fixed dynamics you learned during training.
And this is where the subquadratic graveyard models ultimately failed.
This is the fundamental failure mode.
Yeah.
LTI models are powerful, but they fail at what we call content-based reasoning. They can't adapt to what they're seeing.
Give me a concrete example.
Okay, let's look at the copying task. This is a classic synthetic benchmark. If I tell a model to memorize a word and then repeat it exactly 10 steps later, an LTI model can do that. It's easy.
Why is it easy?
Because it just has to learn a filter that delays the signal by 10 steps.
Yeah.
It's just a matter of timing. It's rhythmic. It doesn't care what the word is, just that it needs to come out 10 steps later.
Okay, simple enough. It's like tapping your foot to a steady beat.
Exactly. But now let's look at a harder task. Selective copying. Suppose I give you a long stream of words, but I tell you, Ignore all the common words like the and a and is, but remember the names of the people. And the names appear at totally random intervals. Sometimes they are 5 words apart, sometimes they are 50 words apart. There's no rhythm.
The LTI model panics.
It completely panics. Because it has a fixed filter, it cannot dynamically decide, hey, this is John, that's a name, I need to write this to my memory, versus this is just the word they, that's noise, I should ignore it. It treats the noise and the signal exactly the same.
It lacks selectivity.
It lacks selectivity. And this is the insight that Gu and Tridow had. They looked at S4, H3, Hyena, all these powerful LTI models, and they said, these are fast, but they are dumb in a very specific way. They can't focus. They can't compress context.
What do you mean compress context?
To match a transformer, a model needs to be able to read a long sequence and distill it down to the important bits. It needs to look at the current token and ask a simple question, is this relevant? If the answer is yes, update the memory state. If the answer is no, keep the state as is and move on.
Which brings us to part 2, the solution. Selective state spaces, or S6. How do they break this LTI curse?
It's actually an elegantly simple idea mathematically, even if the implementation is fiendishly difficult.
Okay.
In previous SSMs, those parameters, the matrices $1 and $2 and another one called delta, or the step size, were constant. They were just numbers learned during training.
Right, the fixed sunglasses 10.
In Mamba, the authors do something radical. They make these parameters functions of the input $6.
Whoa, okay. So for every single token that comes in, the model generates a new custom set of rules for how to handle that specific token.
You got it. The tint of the sunglasses changes for every single thing you look at.
How does it do that?
The Bottleneck matrices, which control how the input affects the state and how the state creates the output, are projected from the input $6 using simple linear layers. But the most interesting one, the real star of the show, is delta.
The step size. Why is delta so important here?
Because in these kinds of continuous systems that we discretize for computers, the step size delta acts as a gate, a very powerful gate.
A gate for what?
Think about it like this. If delta is large, it means the system takes a big step forward in time. It effectively resets the state with the new input. It's a model saying, pay attention, focus on this right now, forget the old stuff.
Okay, so a big delta means remember the current thing. What if delta is small?
If delta is very close to 0, the state barely changes at all. The model effectively ignores the current input and preserves its existing memory. It allows important information from the past to persist untouched.
So delta is the volume knob on the input. It can turn it up to 11 to focus or turn it down to 0 to ignore.
That's the perfect way to think about it. And the paper actually formalizes this in their Theorem 1. They show that this input-dependent discretization of delta functions mathematically, identically, to the gating mechanisms we saw in LSTMs and GRUs back in the day.
Oh, that is a cool callback. So it's like we're borrowing the best part of the LSTM, that ability to selectively forget and remember, and we're injecting it into this much more modern and efficient state space framework?
That is the core innovation. It is what allows the model to filter out stop words or genomic noise while holding on to high-value information indefinitely. It's how it solves the selective copying problem.
But wait, I feel like I'm hearing a record scratch in the background.
You should be. There's a huge catch.
Because you just told me earlier that the only reason these SSMs were fast enough to train in the first place was because they used convolutions.
Right.
And convolutions absolutely require the parameters to be constant. They require LTI.
They do.
But now you're telling me Mamba's entire magic trick is changing its parameters at every single time step.
Which means you lose the convolution. You cannot use the FFT trick anymore. It's gone.
So we're back to recurrence.
You're forced back into recurrence.
Recurrence is slow. We just established this. Sequential processing on a GPU is a death sentence for training speed. So didn't they just solve one problem by creating an even bigger one? Didn't they just break the efficiency, the whole reason for doing this?
This is where the paper shifts from pure math and modeling to hardcore brilliant systems engineering. This is part 3. The scan and hardware awareness. This is arguably where the genius of Gu and Tridow really shines.
Okay, I'm listening.
They knew they couldn't use convolution, and they knew that a naive, simple recurrent loop is far too slow. So they implemented a parallel associative scan.
Parallel associative scan. That sounds like something out of Star Trek. What is it, actually?
It's a classic algorithm, actually, from the early days of parallel computing. It's a way to compute certain types of sequential operations, like a cumulative sum, in parallel. It uses the associativity of matrix multiplication to build a tree-like structure, so you can calculate multiple steps at once. But the real bottleneck wasn't just the math, it was the memory hierarchy of the GPU.
The memory hierarchy. Okay, let's get into that.
Let's do a quick GPU anatomy lesson. You have HBM high bandwidth memory. This is the massive memory pool, like the 80 gigabytes on an A100 GPU. It's huge, but it's relatively slow to access.
Okay.
Then right next to the compute cores, you have SRAM, static RAM. It is tiny megabytes, not gigabytes, but it is lightning fast.
So HBM is the warehouse way out back, and SRAM is the workbench right in front of you.
That's the perfect analogy. In a standard implementation of a recurrent model, you would generate these massive intermediate states. Remember, Mamba expands the dimension of the input. You have a state tensor of size, batch, length, dimension, state size. It's huge.
A lot to carry.
A lot. And if you have to write that huge tensor back and forth to the HBM warehouse at every single step of the calculation, you're dead in the water. The latency, the time it takes to walk back and forth just kills you.
You spend all your time walking to the warehouse and back and no time actually building the product on your workbench.
Exactly. So Mamba does something brilliant. They use kernel fusion. They wrote a custom GPU program, a kernel, that does the whole operation in one go. It loads the parameters A, B, C, delta from the HBM warehouse to the fast SRAM workbench.
Just once.
Just once at the beginning. Then they perform the discretization and the entire recurrent scan entirely inside the SRAM. They never write the intermediate state back to the warehouse.
They keep it all on the workbench.
They do. They only write the final output, the finished product, back to HBM at the very end.
That is incredibly clever. But wait, if they don't store those intermediate states in HBM, what happens during training? When you need to do backpropagation, don't you need those states to calculate the gradients?
You absolutely do. And this is the second trick, which is just as clever, recomputation. They realize that because the scan operation is so blazingly fast when it's all in SRAM, it is actually cheaper and faster to just recalculate the states on the fly during the backward pass than it would be to store them and read them back from slow HBM.
Get out of here. Computing it twice is faster than reading it from memory once.
That is the reality of modern hardware. Compute is cheap. Memory bandwidth is the bottleneck. By optimizing for this memory hierarchy, Mamba's selective scan operation ends up being faster than flash attention 2 for sequence lengths beyond about 2,000 tokens.
So they broke the LTI constraint, lost the powerful convolution trick, but then engineered their way out of that hole with this hardware-aware scan to be even faster than the best transformer implementation.
That's the story. It's an incredible piece of engineering.
Okay, so we have the engine. What does the car look like? Let's talk about the Mamba architecture itself. What are the building blocks?
They kept it incredibly simple, which is another one of its strengths. If you look at previous architectures like H3, they had these complex, heterogeneous blocks with shift SSMs and multiplicative gates and all sorts of things.
A lot of moving parts.
A lot of moving parts. Mamba simplifies all of that. They basically take the standard MLP block from a transformer and the H3 block and merge them into one single homogeneous Mamba block.
One block to rule them all.
It means no attention blocks, no separate MLP blocks. The whole model is just a stack of these identical Mamba blocks.
I'm looking at the diagram in the paper here. It looks like, okay, you have an input, you expand the dimension. That's a classic deep learning move. Make it wider so it can think.
Yep.
Then there is a short convolution. Wait, I thought we got rid of convolutions.
This is just a tiny local 1D convolution, maybe with a kernel size of 3 or 4. It's there just to prevent local disconnectedness, to smooth things out a bit before the main event. It's very cheap and distinct from the global convolution that LTI models use.
Okay, so it's not the main computational engine. So expand multi, short compen. Then the selective SSM, the S6 core we just discussed.
That's the heart of it.
And then a gating mechanism with a swish activation.
Right. It's a very clean, simple, and repeatable block. And another big simplification they made, real numbers.
What do you mean?
Previous SSMs like S4 relied heavily on complex numbers, with imaginary units, to work well, especially for things like audio. Mamba works excellently with just real numbers.
Which I assume makes the compute stack much happier, less of a headache to implement.
Much happier. Complex numbers can be a pain to support across different hardware and with different precision types like bfloat16. This just simplifies everything.
So we have a fast, selective, simplified architecture. But the proof is in the pudding. Does it actually work? Let's move to part 5. The experimental results. The benchmarks.
This is where jaws started to drop when the paper first came out.
Let's start with those synthetic tasks. We talked about selective copying.
Right. As predicted, Mamba solves it easily. The LTI models like S4 and Hyena fail completely, but the really impressive one, the one that made everyone sit up, is the induction heads task.
Explain induction heads for the listeners. What are they and why do they matter?
Induction heads are believed to be the core mechanism that powers in-context learning in large language models. It's the ability of a model to spot a pattern in the context and then repeat it. The classic example is if I show it Harry Potter text wizard and then later I give it the prompt Frodo Baggins back, it knows to complete it with Hobbit. It's copying the format.
It's associative recall. It's learning on the fly from the prompt.
Exactly. Yeah. Now, typically you train models to do this on relatively short sequences. The big question is, does this ability generalize to contexts much longer than what it was trained on?
And what did they find?
The attention-based models, the transformers, they failed to generalize beyond about 2x their training length. Their performance fell off a cliff.
Okay. And Mamba?
Mamba was trained on sequences of length 256. It generalized perfectly to a sequence length of 1 million tokens.
Wait, hold on. Say that again. It was trained on 256 tokens.
Yes.
And it still worked perfectly on a sequence of 1 million.
That is a 4,000x generalization factor. It's almost unbelievable.
How is that even possible? That feels like it breaks some law of machine learning.
It's because the logic of the selection mechanism is invariant to length. The rule it learns is something like, if you see token pattern X, then open the memory gate and store token Y. Then, if you see pattern X again, close the memory gate and output Y. That logic holds whether the gap between the two patterns is 5 tokens or 500,000 tokens. The Mamba state holds on to that key information indefinitely because the delta gate tells it to.
Wow. That is a massive flex. But, okay, synthetic tasks are one thing. What about real-world language modeling? The PILE benchmark.
This is the real test. They trained models scaling from 125 million up to 1.3 billion parameters. They compared against the standard GPT-3 architecture, but also a much stronger baseline they called Transformer plus weight.
What's in Transformer plus weight?
It's basically the modern llama recipe. It has all the latest bells and whistles, rotary embedding, SWID-GLU activations, all the stuff we know makes Transformers better. It's a very strong baseline to compete against.
The strongest. And the result?
Mamba matched the Transformer plus performance, perplexity-wise, at every model scale. And it's significantly outperformed the other RNN-style models like RWKV and RetNet.
And this is with the linear scaling and higher throughput.
With linear scaling. And then they looked at zero-shot downstream tasks, things like common sense reasoning on HelloSwag, PAQA, Wino Grande. Across the board, Mamba was best in class. It was matching the performance of transformers that were twice its size.
Matching a transformer twice its size is a really big deal. That means you can have a smaller, faster, cheaper model doing the same quality of work.
That's the implication. It's a huge win for efficiency.
Now, I want to talk about the DNA section.
Yeah.
Because I feel like this part gets overlooked sometimes in the excitement about language. But to me, it's actually the strongest proof of the selection thesis.
I could not agree more. Genomics is the perfect testbed for this architecture. Because DNA is discrete, it's just A, C, T, G tokens, but the sequences are enormously long, millions, even billions of base pairs. And the signal, the important gene or the regulatory marker, is incredibly sparse. It's a tiny needle hidden in a colossal haystack of what we used to call junk DNA.
It's the ultimate selective copying problem, but for real.
Exactly. So they pre-trained on the human genome. And there's a chart in the paper, figure 4, that blew my mind. They plotted the model's performance, its perplexity, against the sequence length it was evaluating on.
Okay.
For hyena DNA, which is the older convolution-based LTI model, as the sequence got longer and longer, its performance got worse.
Worse. Shouldn't more context always help?
It should, but because hyena is LTI, it can't filter the noise. As you add more context, you are just adding more and more noise that its fixed filter has to blindly process. It actually drowns out the signal.
It gets confused. And Mamba.
For Mamba, as the sequence length increased all the way up to 1 million tokens, its performance got better and better.
It actually used the extra context to make better predictions.
It used it. It was successfully filtering the millions of noise tokens and holding on to the relevant biological signals from far, far away in the sequence. This was then confirmed on a downstream task of great apes classification telling apart human, chimp, and gorilla DNA. Mamba was significantly more accurate precisely because it could handle these long-range dependencies without getting swamped by the noise.
That is absolutely fascinating. It really proves that the selection mechanism isn't just a math trick. It's functionally changing how the model perceives and processes information.
It is. It's a fundamentally different way of handling long sequences.
What about audio? How did it do there?
Audio is interesting. They tested on speech generation and long-form music generation. Mamba outperformed Sashimi, which is the older S4 base model, and also beat a strong diffusion model called DiffWave. So still state-of-the-art.
But I hear a but.
But the authors noted something important here. This was the one domain where using the complex valued parameters, the old S4 way of doing things, still seemed to help a little bit.
Why do you think that is?
The hypothesis is that audio is a continuous signal. It's a wave. It doesn't really have stop words or discrete junk tokens like text or DNA do. Everything is kind of signal. So the aggressive forgetting mechanism of selection might actually be a bit of a hindrance if you aren't careful. You might be throwing away subtle information. But even with real numbers, Mamba still won overall.
So we have a model that matches transformers on text, absolutely dominates them on long context, discrete data like DNA, beats them on audio, and runs faster. Let's just hammer home that speed point again in part 6. Efficiency.
Right, inference throughput. This is crucial for anyone actually deploying these models. Because Mamba is recurrent, it doesn't have a KV cache. Its state size is constant. This means for the same amount of GPU memory, you can fit way larger batch sizes.
How much larger? What's the real-world impact?
They showed 4 to 5 times higher throughput than a highly optimized transformer at a batch size of 128. And the memory usage scales linearly, whereas the transformer's memory usage explodes quadratically. If you are a company serving a model to thousands of users, this is just money in the bank. Lower latency, lower hardware costs.
Okay, I have to play devil's advocate here. This sounds almost too good to be true. If this is so perfect, why are we all still using transformers? What are the blind spots? What are the limitations?
The paper is actually very honest about this. The first and biggest one is scaling. The largest model they tested was around 3 billion parameters.
Which is big, but it's not GPT-4 big.
Exactly. GPT-4 is rumored to be over 1 trillion parameters, a mixture of experts. We simply do not know if the Mamba architecture has some instability or capacity ceiling that kicks in at 7 dB or 100 B parameters.
The emergent properties question.
Yeah.
We know if it gets the same magical abilities at extreme scale.
Right. Transformers just seem to keep getting smarter the bigger they get. Does Mamba have the same scaling law? We hope so, but it remains an open empirical question.
And what about that continuous discrete spectrum you mentioned with audio?
Yeah, I think that's another subtle limitation. Mamba seems to be an architecture that is fantastically optimized for discrete or semi-discrete modalities. Text, code, DNA, things where selection making a hard choice to keep A and discard B is really important. On pure continuous signals, extremely smooth data, it's possible LTI models are actually a better inductive bias. Mamba might be overkill, or the hard gating might introduce artifacts.
It's like using a scalpel when you really need a paintbrush.
A little bit.
Yeah.
But you have to admit, for the vast majority of high-value AI applications right now, language, code, biology, Mamba seems to be hitting the absolute sweet spot.
It really feels like a pivotal moment, the Mamba moment, as we call this deep dive.
It challenges the hegemony. It really does. For the first time since 2017, we have a truly viable alternative architecture that doesn't ask us to compromise on quality to get speed.
Okay, that covers the paper in fantastic detail. But now, it is time for my favorite part of the show. We're going to take these core ideas, Mamba, selective state spaces, the hardware-aware scan, and we are going to extrapolate. It is time for novel notions.
All right, let's hear it. What have you cooked up?
And, of course, the standard disclaimer. The following segment involves speculative research ideas based on the Mamba paper for entertainment purposes only.
Duly noted.
Okay, notion number 1. I call this the life context medical diagnostics engine.
Life context. Okay, I'm intrigued.
So we've established that transformers choke on long context. People try to fix this with retrieval augmented generation, AGOR, but RAG is lossy. You're just retrieving disconnected snippets. You lose the holistic temporal picture.
True. You lose the narrative of the data.
But Mamba improves with context. We saw that with the DNA results. It solved the 1 million token induction head task. Here is the proposal. We train a multimodal Mamba-based model, but not on the internet. We train it specifically and only on the entire longitudinal health record of a single patient. I mean, everything.
Everything.
Every heartbeat from their Apple Watch waveform data, tokenized, their entire genomic sequence from birth, every clinical note, every lab result, every prescription, all concatenated into one single contiguous sequence, billions of tokens representing one life.
A single patient foundation model.
Exactly. And you leverage Mamba's ability to filter noise. Because, let's be honest, 99.99% of your heart rate data throughout your life is normal. It's noise in the context of diagnostic.
It's the stop words of biology.
Exactly. Mamba's selection mechanism, those input-dependent Baller and delta parameters, would learn to ignore the years and years of healthy data while retaining the specific tiny needles in the haystack. Maybe an irregular EKG spike from 5 years ago combined with a specific genetic marker you were born with and a weird lab result from last Tuesday.
And because the model is recurrent, you don't need to reprocess the whole life history every time the patient comes into the clinic.
That's the kicker. It's $1 constant time inference. The patient walks into the ER with chest pain. You feed in their new data, their current vitals, their EKG, and the model just takes one step. It updates its hidden state instantly and says, warning, high probability of acute cardiac event based on a pattern from 2021 combined with this current physiological stressor.
That is incredibly powerful. You're moving from what is essentially snapshot medicine, where a doctor looks at your current state, to stream medicine, where your entire life's context informs the present diagnosis. And Mamba is uniquely better suited for this than a transformer because of that infinite state persistence without the KV cache bloat.
You could actually run this on a server in the hospital.
You could. I love it. It directly leverages the DNA and the audio findings from the paper in a new domain. Okay, what's notion number 2?
Notion number 2. This one is for the robotics and edge computing crowd. I call it the planetary nervous system via Edge Mamba.
That sounds a little ominous.
Bear with me. Right now, in autonomous vehicles, in robotics, we usually have a split stack. You have a perception module, usually a bunch of CNNs that processes the video and LiDAR. Then you have a planning module that takes that perception output and decides what to do.
Right, 2 separate brains.
And if you try to put a big foundation model, like a vision language model, on a drone or in a car, you are fundamentally limited by that KV cache. A transformer model might run out of memory after just a few minutes of high-resolution video context. It effectively has amnesia. It forgets what it saw 10 minutes ago because it can't hold the cache.
This is a huge problem in robotics right now.
The proposal: a single end-to-end Mamba backbone running on local edge hardware. Let's take the example of a drone swarm monitoring a massive forest fire.
Okay, why Mamba specifically for this?
Because it has no KV cache. It has a constant fixed size state. The drone can fly for 4 hours straight, constantly processing its video feed. A transformer would, out of memory, OOM in 5 minutes. Mamba just continues indefinitely.
And it uses the selection mechanism to compress what it's seeing.
Exactly. It would selectively forget the miles and miles of safe, unburnt terrain it flew over an hour ago. That's now noise. But it would remember and keep in its state the wind patterns and heat signatures it saw 3 hours ago on the other side of the ridge, because that's critical for predicting where the fire will spread now.
So it effectively has an infinite attention span on a small battery-powered chip.
Yes. And if you have a swarm of these drones, they are sharing their states. You're creating a distributed, low-power nervous system that never forgets the relevant anomalies, no matter how long the mission lasts or how vast the area is.
That is the subquadratic dream right there. The ability to just keep consuming a stream of data forever without the computational penalty exploding. If Mamba scales to vision as well as it does to text and DNA and early signs from other research suggests it might, that is a very, very plausible future.
So wrapping this all up, what does this all mean? Where do we go from here?
I mean, it really feels like we're at an inflection point.
Are we witnessing the end of the Transformer era?
I wouldn't say the end. Not yet. The Transformer is a resilient beast, and the ecosystem around it is enormous. But Mamba proves, conclusively, that attention isn't the only way to achieve state-of-the-art performance. We might see Mamba layers get absorbed within future transformers, maybe to handle the long context part.
The best of both worlds. A hybrid approach.
A hybrid approach seems very likely, but what Gu and Tridow have definitely done is they've opened the door, they've proven that you can have your cake and eat it too, you can have the quality, and you can have the linear time speed.
And that's a very exciting place for the field to be. If you want to dive into the code yourself, play with the models. The authors have open sourced everything. The link is in the description.
I'd highly recommend it. The kernel fusion code alone is a work of art for anyone interested in high-performance computing.
Until next time, keep your gradients stable and your state spaces selective. This has been TalkTensors.
See you next time.